Swayam Prabha. Digital India. Educated India.
Welcome to module 14 of database management systems. In the last module, we started our discussions on the entity relationship model. We will continue that in this module as well and actually conclude it in the next module. So, these are the items that we had discussed in the last module. In the present one, we will first illustrate the entity relationship diagram notation, that graphical notation for ER model, how nicely this can be shown in terms of certain diagrams, and then we will explore how ER models can be translated to relational schemas, which is a basic step of the logical design. So, these are the topics. So, we start with the ER diagram. Naturally, the first thing to represent in an ER model is the entity set. Every entity set is represented by a rectangle. On the top, we write the name of that entity set. As you can see examples here, the instructor and student are the two entity sets, and below that we write the names of the attributes that are involved, and we underline the attribute or attributes that form the primary key of that entity set. A relationship between two entity sets is represented by a diamond and two connecting lines to the two entity sets. So, here it says that advisor is a relationship between entity set instructor and entity set student, trying to convey the real world situation that students are advised by the instructors, or students have instructors, and so on. As we had mentioned that relationships could also have attributes. So, if the advisor relationship has an attribute date, then it will be tagged to the advisor relationship with the attribute coming as a within a rectangle and attached to the name of the relationship by a dotted line. So, this shows that advisor is the relationship between instructor and student, and the advisor relationship has an attribute date. It is possible that the relationship that hold between two entity sets can use entity sets which are same. That is, it is possible that a set is related to itself. So, as an example, we show the entity set course which has a relationship prerequisite which takes a course ID and relates it to another course ID called the prerequisite ID, because obviously if a course has a prerequisite, then that prerequisite itself is another course ID which must occur in this table itself. So, in this case, if you can see that unlike the earlier case, the prereq ID is not actually a field of this relation course. So, we say these are roles. So, we say the role that prereq relate from the course relation to itself are course ID and prereq ID, where in the actual table both of them relate to course ID, but prereq will pair them to show which course has what prerequisite. And we often need this kind of, we have seen similar instances of this while we dealt with the recursive queries in databases. The source destination of airlines problem that we discussed has similar kind of relationship structure. So, you can think about a relationship flies from the set of source to the set of destination, and basically these two sets, the places, source place and the destination place, are necessarily the same set, the same relation. There could be a constraint on the cardinality. So, the line that links the relationship diamond with the rectangles of the relations, rectangles of the entity sets, those lines could have an arrow at the end or may not have an arrow at the end. So, if it has got an arrow, then it means that, suppose it has an arrow, it means 1, and if it does not have an arrow, if it is simple, then it means many. So, using this notation, we can designate one to one, one to many, these all different kinds of cardinalities that we had discussed. So, for example, if we are showing this arrow on both ends of this relationship advisor, then it means that it is a one to one relationship, because there is an arrow here. So, this is 1, there is an arrow here. So, this is 1, there is an arrow here. So, this is 1, which means that a student is associated with at most one instructor, and it also means that an instructor is associated with at most a student. This may not be a reality, this usually is not the reality, but this we are just showing this as an example. So, if the student instructor relationship, advisor relationship is one to one, then this is how we will denote it. If it is one to many, so which side is 1? This side is 1 and this side is many. So, it is one to many from instructor to student, which says that every student has at most one instructor, and an instructor may have several students. It could be null also, it could be none also. So, for an instructor here there are many students, but for a student here there are only at most one instructor. So, it is one to many, and this is how we designate. A similar thing will happen if I read the same relation in the other direction. So, instructor to student was one to many. So, student to instructor also drawn in the same way, because this is the one side, this is the one side and this is a many side. So, situation is the same. So, if we read from the student to instructor, then it is also designates the many to one relationship. And finally, we can have a many to many relationship, where there is no arrow at either end, which means that an instructor is associated with several, possibly none, no student via the advisor relation, and the student may also have several instructors via the advisor relationship. Now, you can certainly figure out that in the particular case of student instructor scenario of providing advice, one to one as well as many to many are not the usual real world scenarios, but these are we have just using to show you how to model this. Usual scenario would be from instructor to student, it is one to many relationship. A relationship could be total or it could be partial. If one side of the relationship or whichever side of the relationship is total, then we draw a double line. So, you can see here in the diagram we are drawing a double line, which means that in the advisor relationship the involvement of the student is total, which means that every student must feature in the advisor relationship, or in other words every student must have an advisor. But it is partial on the instructor side, because every instructor may not have a student. So, this double line shows that reality. some entities may not participate in any relationship is a partial. Now, these constraints, the cardinality constraints, can be made more precise by actually using numbers. You can actually say on the two sides of the relationship that at the minimum how many entities should relate and at the maximum how many entities can relate. For example, if we are saying that we are on the right hand side here, if you see, we are saying that it is minimum is 1, maximum is 1, which what does it say? It says that every student, the minimum is 1. So, every student must feature in the advisor relationship. So, in real world every student must have an advisor, must have an instructor. It says maximum is 1, which says that every student can have at most one instructor. So, this 1 to 1 dot dot 1 says that every student must have at least one instructor, every student must have at most one instructor. So, together it says that every student must have exactly one instructor. Whereas, if you see on this side, it says that 0 dot dot star, star stands for no limit, it can be anything, any number. So, the minimum is 0, which means that an instructor may not have a student, and star says that the instructor can have any number of student, naturally 0, 1, 2, 3, 4, 200. So, any instructor can advise any number of students. So, these kind of precise number constraints can be put in addition to the one to many or one to one, many to many kind of notations in the diagram. So, when we do that, we have the precise cardinality of the complex relations that exist. Next, we take a look into the handling of the complex attributes. The first, you remember that the first kind of complex attribute is one which is composite, say name, which has first name, middle name, initial, middle initials and last name. So, when we have that, then the way we represent is at the actual name of the attribute is at the outermost level, and its composites are written with certain shift on the left. So, these all say that these are composites of name. So, this says that street, city, state, zip are composites of address, and further indentation say that these are composites of street. So, this is how graphically we show that how complex attributes feature. Now, let us go back to discussing the weak entity sets. In the ER diagram, a weak entity set is represented by a double rectangle. You remember the section is a weak entity set, and why is it so? Because a same course may have two different courses may have the same section ID, semester and year, that is two or more courses may run sections by the same name in the same semester and the year. So, a section cannot be uniquely identified by these three attributes. It needs a relationship with the identifying entity set course to be specific the course ID, so that the entities herein can be uniquely specified. So, since this has happened, so we designate that by putting this double rectangle around the weak entity set section. We underline the discriminator of a weak entity set with dashed line. So, you remember these are the discriminators, because given the identifying attribute in the identifying set, these are the attributes which distinguish different tuples of section. So, they are not shown with solid underline, they are shown as dotted underline, dashed underline. So, that you can make out that this is a weak entity set and these are the discriminators. The relationship set connecting the weak entity set to the identifying strong entity set is also. So, this the moment you have weak entity set, you know that there has to be a relationship to the strong entity set which identifies it. So, that relationship set course which say course ID against this binds that is designated with a double diamond. So, that you know that this is the identifying relationship between a weak entity set and the corresponding strong entity set. And once that happens, then the primary key becomes the discriminators of section, the weak entity set, and the primary key of the identifying a strong entity set, the course. So, that forms our final primary key for this entity set section. Mind you, course ID is not a part of this relation, but it actually plays the role through this section ID as a key for the section relation, without which the section entities in the section cannot be uniquely identified. So, having said that, this is the ER diagram of the university enterprise. Some of the points that you could take a look at. This is the weak entity set we have just seen. This is the relationship to the identifying strong entity set. This is a prerequisite multi-role relationship. This you can see is a total involvement. So, why is it a total involvement? Because every section must have at least one teacher. So, there cannot be a section which does not feature in the teachers relationship. Similarly, every section must get a time slot where the classes for that section is held. So, every section must feature in the sec time slot. So, these are the similarly it must get a classroom. So, these are all different total involvements that we total roles that we can see. We can see some of that elsewhere as well. For example, we can see it here, we can see it here, because in between instructor and the department, the ins department relationship, certainly every instructor must have a department. So, it is total, but it is not the same for the department. Every department may not have instructors. So, this is how, if you can go through carefully, and for example, this is another which is total, which means that every course need a department. You cannot run a course which does not have a department. So, this is how we can see that how the ER diagram, that the first conceptual level diagram of a very simple university enterprise is being designed following the notions and symbols of ER model that we have already developed. Next comes the part where from this model, which is primarily diagram based, we have to really go to the relational schema, which is names of relations and attributes, which is pretty much a straightforward job. So, entity sets and relationship sets have to be represented in terms of relational schema. What is the beauty of the ER model and the relational schema is that when you reduce the entity relationship model to relational schema, both entity sets and relationships sets, both of them turn out to be relational schemas. And so that the database finally can be represented simply as a set of schemas, each one of which must have a set of identifying primary key. So, let us look into that. So, on the strong entity set that reduces to schema with the same attributes is student. So, student has ID, name and total credit. So, which we saw earlier. Now, this gets converted to a schema with ID being the primary key. The other case of weak entity set section, which had the 3 discriminators, and through sec course relationship was identified from the strong entity set course, borrows the primary key of the course to be defined in terms of this relational schema. One moment. This borrows the primary key from here and becomes. So, you can see that in the ER model the section did not have course ID as an attribute, but while we reduce this to the relational schema through this sec course relationship, we have borrowed this primary key from course, the primary key of course, the course ID, and added that to section to make it a complete relational schema. Next comes the representation of relationships. So, we are showing a relationship advisor, so which relates instructors to students. So, naturally every instructor is identified by ID, every student is identified by ID. Since both of the attributes have the same name ID, we are calling them as S underscore ID and for the student and I underscore ID for the instructor. So, the advisor relation is basically a pairing of these two IDs, which gives rise to a relationship which looks like this, relationship schema which looks like this. So, we can in general say that if we have a relationship in the ER model which we want to represent in the schema, then we will create a schema which has the primary key of both the sets and put them together, and if the names clash, we will just change the name with the name of the relation, and that will give us the schema for the relationship, in this case the advisor. So, we have seen how to represent entity sets, weak entity sets and relationships. Let us look at how do we deal with composite attributes, because so far we had assumed that the relational schema has attributes and every attribute has a domain, the type from where its values come. So, if I have a composite attribute where every attribute has a set of components, then the easiest way to handle this is to what is known as flatten the composite attribute. So, flattening basically is, for example, if I take a name, it has 3 components. So, each one of them I can call by given new name, name underscore first name, name underscore middle initial, name underscore last name. By prefixing with the attribute name, I make the names of these components necessarily unique. Now, after I do the prefixing, I might figure out that actually prefixing is not required, first name itself is a unique because it does not occur anywhere else. If it is, then I may drop the prefix name, but in general I can take the attribute name, prefix on the component and just flatten them out, make them all attributes, each separate attribute. So, here when we flatten out, we will have first name, middle initial, last name, as you can see these flattened out from here. Then we have street number, street name, apartment number flattened out from the street. Subsequently, we have city, state, zip flattened out from here. So, all of them flattened out has become separate attributes, and flattening is a very straightforward mechanism by which you can convert complex composite attributes into the regular schema design. You get into a little bit of issue if you have a multi-valued attribute. Multi-valued attribute is one where one attribute may have multiple values at the same time, and the example we talked about is a phone number. I may have multiple phone numbers. So, certainly against an attribute I can keep only one value. So, if my attribute is multiple value, then the basic idea is to use a separate schema to maintain these multiple values. For example, if I have to maintain multiple phone numbers of an instructor, I may have a separate I may decide to have a separate relation which relates the key of the instructor relation and the attribute that I want to maintain multiply. So, in this relationship, in this relation, inst underscore phone, against the same ID I can have different phone numbers. So, there will be different records which match on the ID, but do not match on the phone number, which gives me the different values that the phone number can take. And then this inst phone in conjunction with the instructor relation will actually denote the multi-valued phone number attribute. So, this is just an example showing that for one primary key of an instructor 12222, and there are 2 phone numbers. So, this will basically mean you have 2 tuples in the new relation. So, with that we can handle multi-valued attributes also. Some of the relationships that we may have modeled, which we have done in doing the database ER schema, could have redundancy. For example, take a case here, we have the instructor and we have the student, the advisor relation is incidental here, and we have department. So, we want to say that the instructors belong to certain departments, every instructor belongs to one department, which is the totality of the relationship here. Similarly, every student belongs to a department, totality of the relationship on this side. And inst depth in that context is a relationship which is between instructor and department. Similarly, so we can there is certain redundancy in this, because we can make this simpler if we just take the primary key of this relation and put in here. If we do that, then basically this become redundant, these are no more required. So, all that we are saying is the instructor has a dep name field which says which department does it belong to. So, if there is a choice between whether you will keep such relationships or you will actually reduce the redundancy in the schema and involve the primary key of the other relation into your primary table, which is instructor or the student here. So, instead of creating a schema for relationships at inst department, you will simply add a department name. So, mind you, this is at the ER model level, you did have a separate relationship, but while you reduce it to your relational schema, you are reducing that relationship by including the dep name as an attribute in instructor. So, that is called the reduction of schema, which is often used. For one-to-one relationship, so this is good if you have many to one relation, because this was possible because every instructor has one department. So, if you just include the department name with the instructor, or every student has one department. So, it is possible that way, but if you have a one-to-one relationship, then naturally you can do the similar reduction by choosing the either side as the many, because the unique side has to come on the many side. The unique side here, this is the unique side here, because every instructor has a unique department, and this is the many side here. So, the unique side has to attribute has to come in here, the unique side primary key has to come in here. So, instead of so you can apply the same principle to a one-to-one relationship by treating any one of them as a many side and add the extra attribute on the other side to get rid of this additional schema. The schema corresponding to a relationship set linking a weak entity set to its underlying strong entity set is certainly redundant. We have already seen this. So, this is made redundant by including the primary key of the identifying relation, identifying entity set in the weak entity set. So, that is another reduction of schema that can be done. So, to summarize, we have in this module illustrated the entity relationship diagram, which are very nice ways of graphically representing what we see in the real world, So, it has graphical representation of entity sets, attributes, the key attributes, primary key attributes, the weak entity sets and the relationships, along with the cardinality information. And then we have shown that using certain reduction rules, how we can easily reduce this entity relationship diagram or entity relationship model into the traditional relational schema, and we have seen that both the entity sets as well as the relationship sets become relational schemas.